we'll learn about electric field of continuous charge distribution. Until now, we were talking about discrete charges, that we have charges, suppose in a form of dipole, charges which is discrete system of charges separated by finite distances. But in real life situations, we do have situations wherein we have continuous charge distribution. Say suppose, for example, I have charged this pencil, this pen, which is linear, and if I just assume this to be very thin, and it is just progressing lengthwise, and I have charged this non-conducting rod, a non-conducting pencil, right? So the distribution of charge would be in linear way. And this object is a continuous, okay? So if you look carefully, if you just think in mind, those small bit of particles, right? Those charged particles, they are so closely packed. The distance between those particles, if I try to break this into particles of your imagination, and those charged particles are very closely packed, we can neglect the distances between those charges, particles, but we want to find the electric field at this point because of this linearly charged distributed body at this any point. So this distance at any point of interest is considerably and reasonably large as compared to the distance between the particles. So in this situation, or say if you take the situation of a disk, right? In the disk as well, if you look carefully, if you neglect the thickness of it, it's a sort of like a two-dimensional object, right? And if you charge the disk, which is a non-conducting one, the distribution of the charge would be on a surface. So in this linear object, the distribution was linear. In this one, it would be on a surface. Suppose if you take now a duster, assume this to be of a cuboid shape, a volumetric type of a space which is occupied, a volume is occupied, and you have charged this volumetric object. And now this charge distribution, if you look around and try to figure out, you can say that it is now all across the volume. So it is spaced in a volume. Now if you want to figure out, because of this type of body, at any distance, there is a point P, and you are trying to find the electric field at that point. So what we can assume is, if you take the volumetric to have an elemental volume, because of that elemental volume, what is the elemental electric field? And then if you use the calculus to find the net charge, then you will be able to figure out what is the net electric field because of this volumetric charge distribution. This is what we are going to study today and try to figure out what kind of distribution could be possible. So as we have seen in first situation, that suppose you have a linear charge body, a body which is one-dimensional, and you have charged it, we are neglecting the thickness of it, and the only thing that we are taking into account is the linear distance, right? This distance, the linear distance. So suppose this has a total charge Q, and the distance of this is L. So we can have some measures of the charge distribution. What could be the measure? The measure for this we can write, what is the charge distribution per unit length? And we'll call this lambda. The notation is used. And we will write it here. It's linear charge distribution or linear charge density. So in such body, if you want to figure out that this is lambda, which is linear charge density. Now if you are trying to break this up into differential element, and which is only having length, differential length, so what could be the value of linear charge density? It would be lambda. It could be written as dq is the elemental charge over dl. So this was charge per unit length in terms of differential element. It could be dq over dl. So we can now find from here what it implies. It implies that this dq, which is the elemental charge which is in that particular length, is equal to lambda dl. Okay, and if you integrate this dq, you have to integrate both sides and you will get what? If you integrate dq, it's going to be q, right? So this becomes, upon integration, the net charge, and this is equal to lambda dl. This is what the integration over line that we have done. This is the whole concept and the whole approach that we are going to follow to understand this. So this is one kind of distribution, which is linear distribution of charge, and we got this quantity, linear charge density, and then we have come to know that this is what the dq is, which is differential charge, elemental charge, which is there. dq over dl is what is linear charge density, which is a constant, right, per unit length. And then we followed this to find this relation that we will get for the q. So we have used this calculus. Why? Because it's the continuous distribution, right? It's a continuous distribution. Similarly, if you take another type of object, which is suppose the disk that we have taken, and this disk has a surface. It has a surface. So now if you want to find what is the relation for this, so you can write this q over a now is conventionally denoted by sigma, right? And this we will call surface charge density. Surface charge density. In the differential form, we can write this sigma is dq over dA, elemental area. And similarly it follows. So here, if you take out this dq, it becomes sigma dA. And when you are going to integrate this to find over the surface S, you'll get sigma dA, and here you will get then a q, which is equal to integration upon the area or the surface S. Let us denote this by S. So it becomes sigma dA. So this is what the kind of relation we are getting, that this q, the net charge, is the q charge over here. If you integrate over the surface, it's sigma dA. This relation we get, and this is what the surface charge density relation is, q over a, charge, total charge per unit area. Similarly, if you take volumetric, right, if you take a volumetric here, let me write it here in this portion. If you take a volumetric type of object, similarly we'll have a relation, and here we call this rho, which would be q over v, which is volume charge density. Volume charge density, and this similarly we can, in differential form, we can have dq over dv. Okay, so this rho equals dq over dv, and then from here we can get dq is equal to rho dv. So when we are going to integrate over the volume, so let me integrate it here. So it comes out to be, if you integrate dq over the volume, you will get integration on the other side, rho dv. So the net charge that you are going to get when you integrate over the volume, you will get the net charge which is there in the volumetric kind of object like this. Okay. Now using this concept, we'll try to apply this approach in one of the question, and we'll take an example. Suppose we take an example of a rod, right? And we'll try to understand how we approach to figure out what is the value of the electric field, net electric field of in a situation of continuous charge distributed body when you have this kind of situation. So let us see, suppose you have a rod, right? And this thin rod, which we are considering a one-dimensional object, is placed on x-axis. And the length of the rod is L. And we are placing this in such a way that this is from a point P. Here we are interested to find the net electric field at point P. Suppose this is the origin, and from here to here, this is placed at a distance. AB is that rod, and this A end is placed at a distance x0 from P. We are interested to find what is the net electric field at this point P because of a continuous charge distributed over linearly over this non-conducting rod of length L, and the charge is the given thing, the given quantity is Q, is the total charge, distributed uniformly on a rod of length L. This is what is given, and we are interested to find what is the net electric field at this point. So what should be the approach? First, let's see, if Q is the total charge and L is the length of this rod, then therefore what is lambda? Lambda is Q over L. Also, we need to find what is the differential length. In the differential length dx, what is the dq? What is the charge, elemental charge? Now suppose here we take dx. We have taken an elemental length dx, and in this dx we'll find what is the dq, what is the elemental dq there in this, and because of this elemental dq, what is the elemental electric field at this point? And then we'll move further to integrate to figure out from this point to this point, then what is the total net electric field. So firstly, we'll try to get the equation, get the function. Okay, now suppose this elemental length that we have taken dx is at a distance from here. This is at a distance x, and this is varying continuously. This is what it is. So we know this, that therefore what should be dq? We know this also. Also we have a relation, this lambda is equal to dq over dx, right? If you are taking this to be of this length, or suppose it is dl, whatever, you can take this value. Okay, let's take a dx upon the x-axis, and then we'll put the limit here. So at this point, what is the coordinate? We can write the coordinates here as x0 and x0 0, right? x0 0, and here we'll have x0 plus this length, which is L, and 0. This is what we have the coordinate of this point. So this point has coordinate x0. Why? Because this is at a distance x0 from origin. At here we are interested to find. So this is what we have the information. Another information, if you want to find what is the net electric field here at point P, and this is positive, right? So you write it here, given positive charge. If this is positive, at this point it should be radially out. Okay, it should be radially out, and it should be in the negative I cap direction. Okay, so if you want to find, because of this, what is this value, we can write dE, which is the elemental electric field value. So it is 1 over 2 pi epsilon naught. So elemental electric field at point P, because of elemental length dx, right? We need to write what is dq. So we'll get the dq. This implies that what is dq? We'll get dq is lambda dx, right? So we can write here dq divided by, and what is the distance here? This is x squared. So this is the magnitude, and if you want to find the vector, it will be minus I cap in the direction. So vectorally we can have this equation written, and then after replacing that value we can write dE vector is equal to 1 over 4 pi epsilon naught. It becomes lambda dx over x square minus I cap. Take the minus in the front, so we can write minus in this way, and this is what the equation is. So let me just make it more clear. So dE, which is the elemental electric field because of this elemental dq, is this. This is what we get. If you integrate both sides, you'll be able to figure out what is the net electric field, and when you put the limits, you will get the value. So the net electric field, therefore, net electric field at P will be E net, which is integration of dE. So therefore E net at P, you can write P, is equal to you integrate this, everything is constant, lambda by this is constant, so you take it out, minus remains as it is, it comes out to be 1 over 4 pi epsilon naught. Lambda is there, so let's put it lambda here, and then we can have here integration. Now you can put the limit, it is from x naught to x naught plus L, and then we are left with 1 over x squared dx, and then it is I cap. I cap is showing you the unit vector, showing you the direction of this. This is what, when we evaluate this, we are going to get this value. So take down the steps, and then we will integrate in the next step. We will integrate to find the value in terms of the given quantities. All right, so let me just rub this portion. So I'm writing this equation here. So we are getting the net electric field upon integration, which is electric field at point P is equal to integration with this limit x naught to x naught plus L, 1 over 4 pi epsilon naught, minus is also there, negative, and this comes out to be 1 over x squared lambda dx I cap. So we pull all the constants out, so we will be getting minus lambda by 4 pi epsilon naught integration of 1 over x squared dx I cap here x naught plus L is the limit. Well, if you integrate this, we'll get E net, therefore what is EP, which is a vector quantity, is lambda, and we know lambda, right? What was lambda? Lambda was Q over L. So 4 pi epsilon naught, and we'll write L here. L was given in the question, and when you integrate this, 1 by x raised to the power minus 2, right? So it comes out to be minus 2 plus 1, so it is minus 1, and then it comes in the denominator with a minus sign, so it comes out to be this, x raised to the power minus 1, which is 1 over x, and minus comes here, and then we have the limit x naught plus L. Okay, so let's continue to integrate and get the final expression. We also have a minus sign from previous expression, so we'll keep that minus sign, and then let's see, it is coming out to be, so I'm writing it here, so it comes out to be EP. Let me just demarcate this. EP is equal to minus Q by 4 pi epsilon naught L. All right, so here it comes out to be one by x naught plus L minus 1 by x naught. Okay, and don't forget I cap. I cap is showing you the direction, so this becomes vector. All right, now you can take this in that way, so we will get EP is equal to minus Q by 4 pi epsilon naught L, and then you can just reverse take the negative. If you open the bracket, you can write in this way. It will be 1 over x naught minus 1 by x naught plus L I cap. So therefore we get the final expression as, it comes out to be minus Q or 1 by 4 pi epsilon naught, L is also there, and then this comes out to be x naught plus L minus x naught. If you simplify this, it is x naught times x naught plus L. This is what we get. X naught gets cancelled, and then this L you can cancel it out. So finally we are getting this in this way. So therefore the final expression is the net electric field at point P, which is at the origin, is going radially out towards the negative x-axis, and this has been shown here in this way, which is minus Q 4 pi epsilon naught times, this comes out to be 1 by x naught plus L. I cap. So this is the final expression that we get. Now if you consider this point of interest P to be very far off as compared to the length of the rod, then we can in the denominator make that approximation. You can put that L to 0, and then this would become x squared here, right? It would become x squared. So let us take that approximation. Let us take the approximation. We can take this as an approximation if this x naught is very much greater than L, right? So in the denominator we can put that to 0, and therefore we'll get EP is equal to minus 1 over 4 pi epsilon naught Q, which is the net charge, and in the denominator it would become x naught squared I cap. Now look carefully. Is it not the situation of a point charge? So that approximation is reasonably correct. Why? When we take that continuous charge distribution, the length of it is small as compared to the distance far off at any point P. And if you take that approximation, so that length of the rod would behave as it is a point. And we know by our previous understanding that electric field, because of a point charge, is of the same value, same expression. So this is what we get. We have applied this concept of linear charge density and we are able to find this expression. Excellent.